And now on to the next part of our discussion on wave motion. We have sound intensity. Put loosely, sound intensity has something to do with how loud or how strong the sound wave is. Since sound is a wave that travels in all directions away from the source, you have a source of sound, and the sound wave travels in all directions away from the source. Sound intensity may be defined as I is equal to P over A, where P is power of the source and A is surface area of radius R upon which the sound is spread out. So if you look at this point, the sound wave is spread out on a surface area of radius R. If you look at a different point, then the radius R for that point, that's R for the surface area A. So if you have R1, then you have surface area A1. If you have A2, surface area A2. Now, typically, the surface area is surface area of a sphere, but in some instances, it will depend upon the problem. It will depend on how the sound wave has traveled away from the source. If the sound wave is traveling in all directions, think of this in terms of 3 dimensions, the sound wave is traveling outwards, forming a spherical shell. The sound wave is spread out on the surface area of a sphere. And that's typically the surface area of radius R. I is the sound intensity at a distance R from the source. I is equal to P over A. P is in watts. A is in meter squared. So the unit for sound intensity I is watts per meter squared. Again, intensity I is equal to P over A for sound, a wave that travels in all directions away from the source. The intensity equation shows that the farther away from the source, the weaker the intensity of sound gets. I is equal to P over A. The farther away from the source, the bigger the area A. The bigger the radius R gets, the bigger the surface area A. The bigger the denominator, the smaller the intensity gets. I is equal to P over A. Now, consider 2 points from the source. We have the source of the sound wave. The sound wave is traveling in all directions away from the source. Let's consider 2 points. Point 1, radius R1 from the source. Point 2, radius R2 from the source. At the first point, you have intensity I1. At the second point, you have intensity I2. First, let's take a look at intensity I1. I1 is equal to P over A1. Surface area for a sphere of radius R1 is given by 4 pi R1 squared. So I1 is equal to P over 4 pi R1 squared. Isolating P, we have P is equal to 4 pi R1 squared I1. Doing the same thing for point 2 for intensity I2. I2 is equal to P over A2. surface area A2 is given by 4 pi R2 squared. I2 is equal to P over 4 pi R2 squared. Isolating power of the source, P is equal to 4 pi R2 squared I2. Now, we are considering 2 points, point 1 and point 2, but there's only one source, meaning there's only one power. So, P here is the same as P here, equating the two equations. We have 4 pi R1 squared I1 is equal to 4 pi R2 squared I2. Canceling out 4 and pi. And rearranging, we get the following equation. I1 over I2 is equal to R2 squared over R1 squared. This equation is known as the inverse square law. The inverse square law tells us that if we know the intensity at one point, we can determine the intensity at another point even without knowing the power of the source. I1 over I2 is equal to R2 squared over R1 squared, the inverse square law. If we know I1, we know R1, and we know R2, we are able to determine I2, even without knowing the power of the source, even without knowing power P. That's basically what inverse square law tells us. Now, sound intensity is often expressed in terms of the decibel scale. We have beta is equal to 10 dB log of I over I naught. Beta is referred to as the sound level. Unit is decibel, dB. Beta is equal to 10 decibels log of I over I naught. I is the intensity of the sound wave. Beta is the sound level of the sound wave with intensity I. Sound level beta basically compares the intensity of the wave I with I naught. A reference intensity, I naught is the lowest intensity that may be heard by the average human. I naught is equal to 1 times 10 to the negative 12 watts per meter squared. Here are some sample values for sound level beta. Beta, hearing threshold is 0 decibel. The hearing threshold or threshold of hearing is the lowest sound level that may be heard by the average human. Then we have normal conversation. Beta is 60 decibels. And pain threshold, beta is 120 decibels. Pain threshold is the sound level at which the sound is very painful to our ears, to the human ear. We can consider the pain threshold to be the highest sound level that may be heard by the average human. Sound with sound level greater than 120 decibels may still be heard, but the human ear will already suffer some damage because the sound is already too strong or too loud. For instance, for a jet engine, the sound level is 130 decibels. This sound may still be heard by the average human, but the person will suffer hearing damage if exposed to this sound for a long time, for longer than a certain period of time. That's because 130 decibel is greater than the pain threshold. You have sound level beta. Beta is 10 decibel log of I over I naught. For sound to be heard, two conditions must be met. The intensity must be greater than I naught, that is to say, the sound level must be greater than 0 decibel, and the frequency of the sound must fall within what is referred to as the audible range of human hearing. And that's from 20 Hz to 20,000 Hz. Audible frequency is greater than or equal to 20 Hz, but less than or equal to 20,000 Hz. So, audible range of human hearing from 20 Hz to 20,000 Hz. Sound of frequency lower than 20 Hz is referred to as infrasound, while sound of frequency greater than 20,000 Hz is called ultrasound. So let's have the following problem. We have sample problem number 7. The intensity of a sound is 135 microwatts per meter squared at a point 4.20 meters from the source. What is the power of the sound source? And what is the sound level of the wave at a point 10 meters from the source? So we have 2 points to consider. Point 1, point 4.2 meters from the source. Let that be R1. Radius 4.1. R1 is 4.20 meters. And then we have the second point, point 2, a point 10 meters from the source. R2 is equal to 10 meters. At R1, the intensity of the sound is given 135 microwatts per meter squared. So that's I1. I1 is equal to 135 times 10 to the negative 6 watts per meter squared. We know the intensity reference, the reference intensity rather, I naught. I naught is 1 times 10 to the negative 12 watts per meter squared. And we are looking for power of the source and the sound level at point 2 at radius R2. We are looking for beta 2. For sound wave, we know the intensity to be I is equal to P over A. Isolating P, P is equal to I A. For point 1, for radius R1, we have P is equal to I1, A1. And A1 is surface area of a sphere of radius R1. We have 4 pi R1 squared. Plotting in the values, the known values, we see that the equation is complete. We are able to calculate the power of the source. P is equal to 0.030 watts. Using now the inverse square law, we have I1 over I2 is equal to R2 squared over R1 squared. We know I1, we know R2, and we know R1, the only unknown is I2, we are able to determine the value of intensity I2. 2.3814 times 10 to the negative 5 watts per meter squared. Using the equation for sound level, beta is equal to 10 decibel log of I over I naught. We are able to determine the sound level beta 2 because now we have determined I2. The equation is complete. We are able to calculate the sound level beta 2, 73.768 decibels. The sound level at a point 10 meters from the source. And that's it for now. That's it for our discussion on sound intensity. We'll continue our discussion on wave motion in the next video. In the next video, we'll take a look at the concept of Doppler effect. So again, that's it for now. Thank you for watching.